build anything out there, then you can claim it. Like there's a oil well somewhere, I think it's so many miles offshore, and somebody bought it and then claimed it as a sovereign nation.
$200 million.
Of course they did.
Yeah, totally did.
So what is NUMPY anyway?
That's what we're going to talk about right now. Thanks for asking. All right. So, yeah. So NUMPY stands for Numerical Python, and it is a library that is not a standard library, but it's such a widely used library that that it's almost ubiquitous. People use it a lot. It actually has a website. Oh, here it is. Here's the website. So numpy.org will take you to the website. Numpy.org is the fundamental package for scientific computing in Python. And so what do we use it for? Well, probably the primary reason is that it includes this, what they call a powerful, right? They created so they can add cool adjectives to it. N-dimensional, meaning it can have as many dimensions as you want, array object. So what is an array? Well, in computer science, an array is an entity that has that has a sequence of entities that are all the same value. So they all have the same data type. So you can kind of think of it like a list, but every item in the array is of the same data type. So you always can say, I've got an array. Somebody might ask, an array of what? Well, you can say an array of integers, or an array of strings, or an array of floating point numbers. Every single element is the same. Now, you can have a one-dimensional array, which means that it's just simply a sequence of whatever they are. Let's say they're numbers. It's a sequence of numbers. And it's a lot like a list in that case. Okay. You can also have a two-dimensional array, which means there are rows and columns of numbers. So later, when we get into rasters, there are tools for taking a raster data set and converting it into a two-dimensional array, because a raster is simply a set of rows and columns of data. Okay, so that's what a two-dimensional array is. You can have a three-dimensional array. A three-dimensional array can be rows and columns, and then I don't know what you would call it, layers, rows, columns, and layers of a data set. So that might represent a multi-band. Have you all taken remote sensing, or?
Yeah, is that what we're taking now? Remote
Okay.
sensing.
So you could represent all the numbers in a Landsat data set as a three-dimensional array. Rows, columns, layers, or bands is what it's usually called in remote sensing. Okay. Now, you can actually have four-dimensional objects. Rows, columns, layers. And what could the fourth dimension be? I'll tell you what it usually is. Time. Yeah. So you could say, you could reference an individual item as the row, column, layer, and time. So in other words, if you had multiple Landsat data sets of the same area, you could say row, column, data, time to get a specific value in there. Right? You could have another dimension. Okay, you could keep adding dimensions, but it's kind of hard for our brains to wrap around. Well, what's a 7-dimension object?
Could it be a position?
The position it's already implied in the row and the column. Usually, like if we're talking about geographic data, the row and the column corresponds with a location on the Earth. But yeah, I mean, you could, like if you had rows, columns, band number, time, you could also have some other variable that existed, like.
You have to visualize that. Can you visualize that? Because it's not a physical thing, right?
No, in fact, it's really hard to visualize anything over. Well, it becomes hard as soon as you get past 2 dimensions, because we're used to visualizing things that are on screens. So if you have rows and columns, which the screen has, you have screens, right? So there are ways to, like, you can start including a slider bar to, like, take you through time, or a slider bar to take you through depth. If you had layers that represent, so you can red, green, blue, or you can actually mix the 3 bands, red, green, and blue. If those are the 3 bands, you can mix those together and show a combination of the color. There are ways to show that 3rd dimension, and even a few ways to show the 4th dimension. But yeah, once you get into, like, the 5th, the 6th, it's not really intuitive to show it on a screen.
So a 3D printer is just 3D. There's no such thing as a 4D or 5D printer.
Well, you could argue, like, what if the printer, because most 3D printers don't change the object, they just lay down material, right? You've seen a 3D printer work.
Right.
They lay down material. Well, if they could also change the color that it was in a certain position, then that would be an example of 4D, because it would do the height, the width, and the color at a particular location.
So everything that's unique is not the same as any of the old positions. That would be a dimension.
Yeah.
That could be on them.
Yeah, you could do on you can. NumPy will allow you to create an array object of however many dimensions you want. But what I'm telling you is, dealing with geographic data, the most you're going to get to is probably 4. Okay, 4 dimensions. Okay. There are file formats. You guys ever dealt with NetCDF data? Anybody? Okay. So this maybe I'm getting a little bit off track, but here at arcgis.com, if you've ever been there before. So here's an example of some 4-dimensional data. I'm going to map.
Using the NumPy is what allows you to have multiple dimensions, right?
It allows you to create a data type that represents multiple dimensions. So I'm going to add putting atlas. All right, so I got my seawater temperature map here. And you'll notice that there are 2 slider bars that it throws up here. This slider bar right here, which looks ugly, I mean, it's ESRI's fault. They should make it look better. But this slider bar represents the depth. So this is 0, meaning at the surface. So this is the seawater temperature. But if I go down, then I'm looking at a different slice. So down further, it's colder, 250, I don't know if it's feet, it's probably meters, 250 meters below. Notice all this stuff, there's no data there. Why? Because it's probably less than 250 meters down there. There's a shelf that comes off of here. So if we go, way down here, we would expect to see only those areas that are that deep. So there's data there. Go up, right? So there's the surface again. Now this slider that ESRI has put on there, I can go through time. So here is a different time period. September 29th. Here's October 6th. You can see how the pattern changes there a little bit as I move that around. Go back to September 12th. I can see. And we could even hit this little play button, and going through the internet, it's not really present. But yeah, what it's doing is it's loading up them, but because the internet is kind of slow, it's probably taking as long to draw as it is to go on to the next one. So you don't really see anything interesting.
Well, one thing you can visualize is that yellow area is the equator line closer to the sun, and so it's warmer.
Oh yeah, of course. But what I'm trying to say is this map actually isn't refreshing because it's going through the internet. But if you wait a second, move it and wait a second, it'll actually change. But the animation button isn't working really well because it's taking longer than the refresh time before it requests another one, and then it has to say, okay, give me the next one. I guess maybe you could change this to.
Were you running through internet or local?
This is all internet because I don't have. This data set is humongous. It's really, really big. Each time you think about it is has the rows and columns and then all those depth values from 0 all the way to 4,000 meters. So there's like tons and tons of data there. So I was just trying to show you an example of.
So you could do like soil layers with that too. Like
you could do soil layers with that if you had that data. Yeah. So like this, there are the U.S. government has floats all throughout the world that are measuring sea surface temperature, and they're actually correlating those with satellite measurements. So in other words, and then they're creating this all in real time. So in other words, there's all these floats that are floating out here on the water. They're measuring sea surface temperature, and then I also have satellites that have thermal infrared sensors that are taking the temperature, but they become miscalibrated because basically due to atmospheric conditions, 35 might represent 85 degrees Celsius one day, and because of atmospheric data, it might not be the same number the next day. So you tie the in-field measurements to the satellite measurements every day, and you can create a map like this. And so the U.S. government puts this out. It's called HICOM data. They put this out every day, or every 3 hours they actually put it out. Every 3 hours they put it out, and then they also predict out 24 hours what the sea surface temperature and the
and they storing all the information, or they just give it to you live real time? How long they keep that? Because you can petabytes, terabytes of data.
I don't know. I do know that they archive it, at least for a time.
Right.
And so you can actually download all the data, ICOM data download if you really wanted to. Have
you seen that? Do you ever get on like Esri, like the training?
Yeah.
Have you seen that space-time viewpoint that they posted us?
Is that the one that what data do they use?
You can like map like temporal data, and it'll like you can find like hotspots like of patterns.
Yes.
It's pretty cool.
Yep. Yeah, I've seen a demo of that training, but I haven't actually done that training. Okay, so I was just trying to show you some data where you might use something like that, but that would be more like the data's. So for our applications, the data might be in our GIS, but we might want to manipulate it and find a particular thing. Well, we could use a NumPy object for that. So another thing that NumPy allows you to do, or NumPy or NumPy, depending on how you want to pronounce it, is that it has these sophisticated broadcasting functions. So similar to what we just demonstrated earlier, where we could take the value in one field and add it to the value in another. If you have two arrays that are the same dimension, you can do things like add them together, or subtract them from each other, or do math on everything. You can even do like an if-then statement through lots of things. So you might say, if the value in this array is equal to 7, make the value in this array equal to this array times that array. So you can do a little bit of if-then statements in there, and those type of functions where you can basically take one array and do a mathematical or logical operation on it and put it into a different array. Those are called broadcasting functions. So that's what it means by sophisticated broadcasting functions. And we'll show some examples of those over time. Probably some today and some later on. And these other two we're probably not going to do too much of, tools for integrating C++ and Fortran code. So NumPy is actually written in C++, and so as part of releasing this this tool that you can use, they have also created some ways that you can actually write C++ code, which runs faster than Python code, and integrate it right with NumPy. But that's not going to be part of the scope of this course. Fortran is an older programming language. It's still in I wouldn't say wide use, but it's still used, particularly in the scientific field. And then there's some more advanced math capabilities that it has there. Now, Python is part of a larger set of libraries called Scientific Python. So I'm not sure how to get to the and we'll cover a few of these. Scientific Python. See if we can get there. Yep. Okay. So scipy.org. So NumPy is just one of these tools. It's kind of like the foundational one. So NumPy allows you to have these n-dimensional arrays, and then these other packages, in one of which is IPython. So these guys, that's open source software, they've created all these packages. So NumPy is the foundational one that has the n-dimensional array package. Then they have another package for like visualizing arrays. That's called matplotlib. They have another package for doing scientific functions like statistics and things like that. So I cover a little bit of this in my graduate 715 course. We talk about that a little bit. And then we've used interactive Python before. That's another one that they create. And then finally there's pandas. And pandas allows you to manipulate data really quickly. And it actually has a lot of tools that ArcGIS, like if you wanted to do a select, pandas can take a data frame, which is what it calls a table, and do a select on it and return the results. It also allows you to really quickly add additional fields into a table, things like that. So we'll talk about pandas as well eventually, but today we're gonna start with NumPy. So this is where we were before. The reason that I'm going to show you this, and I'll switch gears back to this now, is that ArcGIS allows you to convert your vector and raster data into NumPy arrays. You might ask, why would I do that? Well, there are some analysis that you just can do better in NumPy than you can using ArcGIS. And even those things that you could do better inside of ArcGIS, it might be a lot faster, or maybe you're more comfortable in doing ArcGIS. It might be a lot faster to do it in NumPy. For example, what we did today was calculate the mean of all of the magnitude field variables, right? So we could do that in NumPy as well. So we'll kind of demonstrate that. So the first thing to do that is if we go back to the data analysis module, there are a number of functions, and I talked to you about, whoops, functions. No. I talked to you about describe, but this is the one that I want to talk about today, and that's the feature class to NumPy array. So what this does is it converts a feature class. Now, feature class is just ArcGIS's lingo for a GIS data set. Okay, points, lines, polygons, even a table. So it can convert a feature class to a NumPy array. So let's do this, and then we'll start to see what this NumPy array is. Okay. So if you look at what it requests almost the same thing that either a search cursor or an update cursor requests. By the way, we didn't actually get to covering insert cursor. Just as a side note here, we'll probably come back to it next week. But insert cursor allows you to put new rows in a table. Okay. All right. So so the syntax for doing this feature class and NumPy array is almost exactly the same thing, and it's because it's returning a very similar thing. A cursor is just a representation of a table, and when we get this NumPy array back, it's also a representation of the table. It's a little bit different type of object. Instead of returning an ESRI cursor, it's going to return this NumPy array thing. So we need to learn about what a NumPy array is a little bit more. But that's what it's doing. So it's still asking us, what table do you want to convert into an NumPy array? That's what this is. And so you need to give it the path to the table. You still need to specify what field names you want, because it won't just return all of them. You can optionally specify a where clause, a spatial reference. You can specify if you want to get a separate row for every single point. That's not that common. You can specify whether you want to skip nulls, and then you can specify individually what null value, what represents a null value. So we'll look at all of these here. So let's. I'm actually going to go back to week 6. By the way, this is all updated now on GitHub. I updated it in between, but I'm going to edit this in IDLE right here. So this is my. Actually, I don't like this one as much as my update cursor one, because this one I made the table. Okay, I'm just going to get rid of all this. I'm gonna all this and all. So this is going to be just this. So all I have, I created a variable called table, and it represents the path to my tornadoes data set, right? So I got the path to my tornado data set, and I still got that stuff about the spatial reference. And notice that what I can do, instead of update cursor, I'm gonna save this before I forget. I'm gonna save this as something else. So instead of update cursor, I'm gonna call this table to. Actually, I'll just call this NumPy. NumPy 1. I'll call it 2 NumPy 1. All right. So instead of saying update cursor, what I want to do is get the NumPy array feature class to NumPy array, and other than that, the signature. This is called the signature. In other words, the parameters and the parameters in their order is almost identical. I think it is identical. So I've got the table, I've got the field names, I got the where clause, and the spatial reference. Yep, that's the same order. So I'm all set. So now rows will equal a NumPy array instead of being a search cursor. That's the only difference here. So now I could print. I'm going to print rows here and run this. Now if I run that, I'm not going to get something that's actually really easy to visualize. Okay. But that's my NumPy array that it just returned, and it's a mess. Like it keeps growing because it's huge. So it's continuing to grow. Okay. So it's hard to tell that this is a NumPy array, but it is, and we don't see the top of it, but we can still see the components of the NumPy array. See, this is one item in the NumPy array, right? One of its constituent pieces. So we can tell that we're still almost have the exact same information, right? This is the object ID. This is the centroid still, and now it's in latitude and longitude. This is the next field. I forgot what it is. I think it's the FID. That's the that O month field. This is the year. That's the month. That's the date, and so on, all the way down to that field we created, that magnitude field. Okay. So we have it, and it looks reasonable. It looks like it has a reasonable set of values. Okay. Now, I'm just going to print. I'm going to rename it because I don't want to call it rows now because it isn't the same thing. So I'm just going to call this an array, an NP array. But instead of printing the n array, I'm going to print the type of the n array. I'm also going to import numpy so that I have it. Like, it'll actually return an numpy array even though I haven't imported it because I have it in the system. But it won't let me actually manipulate anything or call on any of the functions until I import it. Now, most of the help that's on the numpy website does this. So if you here I'll show you. If you want to go to the numpy website and you want to run one of the functions, let's see, documentation. Where's the numpy tutorial? Maybe. So if you want to run this function that's going to get the size, I don't see it. Oh yeah, yep. So if you want to run this example that's listed here, that basically just reshapes an array, we don't really need to do that. Here it gets the size. Then you need to import numpy as np because everywhere in their code they just call numpy np. See how they do that? It's just shorthand. I'm just telling you how to use their help. So you could not say that. You could just say import numpy, but then you have to apply numpy. You have to change all of their example code to numpy dot. Okay, it's not a big deal. It's just that's the way it works. All right, so I'm going to run this, and this time it's going to run. It's not going to print the entire. Shouldn't print the entire. There it is. Okay. So it's telling us that it is a numpy nd array. That's what it is. That's what it is. Okay. So if we want to get the size of our array, there's an example there. We can get the size in here by saying, nd array. So since it's an object, it has methods. So we can say size, and it's a function, right? So see, oh no, it's not a function. I guess it's just a property of the object, not a.
Working that too?
Well, I don't know. We could test that out. Size is doing the same thing as that. So it's telling us that there are 4,100.41273. I'm pretty sure we could open up our GIS Pro and see if there's that many. Sorry, I know we're going a little bit late. I won't go much longer. We'll cover some of this more next week or next time we meet. Okay. Let's see how many there are. If we open up the attribute table, it says 41273, right? Okay. So this number here, that size, must be telling us how big it is, right? Not necessarily how many items we have in our array. Sorry, that is how many items we have in our array. And you ask if we can do len of, what was the name of the variable? An array? I don't know. Yes. Okay, we can do the same thing. So that works as well. But if it was multidimensional, I don't think that would work. But because our array is a one-dimensional array, we can do that. So the array that we have is a one-dimensional array, and every item is actually a record. Okay, and so this special type of array is called a record array. It's a record array. So every item is a record, and we can access the individual elements in the array by almost like as if they were a dictionary. So if I want to get just the magnitude, I can say, what? I'm at the interactive terminal, so I can say n array, and then use this bracket, and say the name of the field. So here, I'm getting a big array, and this is the way it prints it. I'm getting a big array of only the magnitude values. So now I have 1, 2, 0, 0, 0. So it's giving them all to me, but the way that it prints it out in Python is that it only shows me the first 3 and the last 3 if there's like more than 100, I think. So now I've gotten just the magnitude values. So I can do some of these functions that exist inside of Python. I'm sorry, inside of NumPy. Like I could get the max or the min or the standard deviation of those values. Okay, so I could say n array, and then say the magnitude, and then I forget what the name of the function is. So if you want to know what it is, you can always Google. So it's numpy.mean, and then you give it the array. So it's actually like this. numpy.mean.
You want me to put NP?
Because I said import NP, so you're right, I should do that. So that's the mean. Now that number looks a little different. That number looks like the way we did it the first time, where we didn't throw out the zeros and the negative ones. Okay? So what if we wanted to make it so that we didn't have the zeros and the negative ones? Well, there's a few ways we could do that. One way is to specify that in the where clause. So we could go back over to here, and instead of saying, we could say where mag is greater than 1. No. Is it greater than or equal to? So it's greater than 0. So now if I run this, and then I rerun this. Now I only have the records that are greater than negative 1, and so now I have the proper value for that year. I think I actually said greater than 1 in my other example, which I shouldn't have. I should have said 0, I guess, but this one works. There we go. Yeah, that's the same number we got before. So I get the mean of that value really quickly. I mean, if I wanted to change my code so that I did the same thing as I did before, then I could do something like this in a lot less code. So I'm actually going to print this. Print mean. And then I could do and year equal to 1970. There we go. So that's just 1970. And so if I wanted to make this even more simple, format, not for year in range 1970 through 2017, or 2018 is what we decided was last year. And then I could also print year, comma. All right. So now we run this. Oops. Need a colon, indent it. I want to get rid of that. I don't know why that's part of this, so let's close that. Okay. Empty slice year. Oh, because I did 19. Sorry. So there was some invalid values. The zeros. 2017 for year in range. Oh, I didn't print this. I gotta put that inside the loop. Remember that was inside the loop before. Okay, so now what this is going to do is it's going to go through and calculate that for all the years.
That was the mean value.
That's the mean value. Yes, of all the ones greater than 1. So that code is a lot less code, first of all, and it ran a lot faster than accessing the individual values row by row, because we first, as long as we're not concerned with the data itself, in other words, we're not concerned with changing any of the values or really inspecting the values, it's often faster to use NumPy to get the data, and then this mean function is already built in to NumPy. And so we could do something like.
Are you using less code to say the same thing?
Yep, and it's kind of powerful because we can build on it. Who's taking a statistics course? You understand what a z-score is,
Yes.
right?
It's been a while, but yeah.
So what it, like if I say,
Standard deviation stuff.
yeah, it's standard deviation stuff. So yeah, well, okay, I'll boil it down. So we have a bunch of numbers, right, that represent here. These numbers right here represent the average magnitude per year, right?
Mm-hmm.
But it's kind of hard to tell, which ones are the weirdest values. They're all 2s, right?
Right.
So it would be interesting to find out how different they were than the average value, right? Like that would be more interesting than just finding out what the number itself was. It'd be almost more interesting to find out how different it was than average. That would be more significant. And so that's one step towards a z-score. So we'll just do that one step and then talk about that later. So I have the magnitude right here. That's the mean. Sorry, I have the mean right here. I could also report the mean minus the mean for the whole thing. So that would be like this. So
The mean total.
yeah, so if I have my ND array, and I could just say, whoops, overall mean is going to equal this. So I've got my mean for this array, but I need to go make sure that I don't have my year associated with that. I lost the end there. Okay. So now my overall mean is going to be, I can calculate it easily as the mean from this entire data set, and then I can get all the individual data sets and just subtract the overall mean. Would that be right? Like, yeah, because if this number is bigger, then this will be positive. If that number is smaller, then, in other words, if this number is smaller than the overall mean, then it will be negative. And I actually want this. There we go. All right. So now I can run this. Whoops. I kind of lost track of all my print. This opens this mean. I need to close that mean. That should work. So now I've printed the mean, but I'm also going to print how different it is from the overall mean, which is probably more interesting. So now I've got like, let's see, what's the biggest number here?
1.9.
Yeah, that 1.9.
This one right here?
No, up more.
1.19.
Well, up like 5 more.
So,
Some more.
19.
Oh yeah, right there. So 1974, that was the year that we noticed before, but that was much higher than usual. This is kind of on the other end, much lower than usual. But all these ones that are like really close to 0, are there any double zeros? No. Well, yeah, this one. 2007 was a very typical year, okay, in terms of the tornado intensity. But the tornado intensity was less in other places. So to get the z-score, we'd have to actually also get the standard deviation, because we're concerned with how many standard deviations it is off the mean. Okay. So that would be the next step. That'd probably be even more interesting, because basically once we have that, we could say, okay, assuming that the distribution of the tornado intensity is normal. And in fact, one of the things about the way we did it, taking the mean of a mean, is that we can almost be positive that the average annual intensity over an entire year is going to be a normal distribution, because we're taking the average on an average. So anyway, we could figure out how unusual it was. So in other words, if it's 1.5 standard deviations away, we know that type of year only happens once every like 70 something, because the standard deviation curve, the normal curve is known. So we can figure out the area under that curve, and we could say,
isn't 2 standard deviations like 98%?
yes.
Okay.
So if we got a 2 standard deviation value, we could do that. In fact, I don't know what it is, but my guess is that it's just called this. I could look it up, maybe. Well, let's see what it is. Overall S2D. All right. Yeah. What's that value? Standard div. Okay. P st dev is std. Okay. All right. So that should work, and we could say. Well, anyway, since we're running so late here, I don't want to keep you all forever. But what we would do to get so that's the standard deviation. The standard deviation is 0.58. That's one standard deviation. So that, in fact, none of these values are that unusual, right? At least for the years that we looked at.
Right.
So none of them are way over, way above one standard deviation. So they're they're all pretty normal years. That's one standard deviation. But if we wanted to actually calculate that, we could take this value and compare it to all of those values and find out what percentage of a standard deviation it was. Then we could look at the z-tables and figure out what the area under the curve was. So we could figure out the probability of that happening any given year.
So this would be like a very narrow bell curve, a very steep one, because they're not that far off of the standard deviation.
Well, the distribution of these values is definitely pretty narrow. Yeah. So that's 0.58, and none of our values were there.
Well, you know, when you got that many numbers and the value like that, scientists probably want to know. The only way you do it is do it like we was doing and kind of, you know, put a number there and say, hey, if it pops over one, you know, it's unusual because all these numbers are the same.
Right.
So you want to be able to get a difference and they explain.
The 17 had a pretty active year too, actually,
Yeah.
compared to the rest of them.
And so the real power of doing this is that the real power of using NumPy in this case is that they have taken care of writing a lot of these functions that you would use commonly for you, and they run really fast because they're actually not running in native Python. They're running in C, and you can access them. You don't have to calculate mean yourself. But you can see we still had to have a loop. There wouldn't really be a way to do this without a loop. Maybe if we use pandas, we could do it without a loop, which we'll get into pandas later. But you know, we still have if statements. There's still the same logical operators in our code in order to get it to work. Actually, we don't have an if statement, but we're still doing some condition, right? This is still a condition that we're specifying. So our ND array is changing every time through the loop. So we don't have an if statement.
But you run it through a range of years, so only you can do that.
Yeah.
You gotta have that force it.
Yeah, we gotta have a loop to do that. Now we could put the loop inside. We could have actually taken this array that we got the overall array, and we could have instead of doing that here, we could have put the loop after we got the array and looped through the array and made some selections, which I did want to show, but I'll show that on a different week because it's already like 4:30 is the latest we can normally get out of class. So. All right, and also I want to put the stuff on all the computers, but I'll be here to answer any questions, and I will be here tomorrow too. Yeah.
Are you getting here early at all tomorrow, or are you coming like right after class?
Is there a class before?
I don't think
tomorrow?
on Wednesday. No.
Okay, I'll try to get here. I do have a meeting at 9, but it should last about a half hour at the longest. So if I leave by 9:30, then I will get here by. It takes about an hour and 15 minutes. What's that?
From 9:30? Yeah, 10:45.
10:45.
If you don't have no traffic, no breakdown.
But tomorrow's the 417 class won't last as long.
Oh, okay.
Oh yeah, for sure.
We are gonna go over the tests and have a lecture, but
Oh, they're graded already? Awesome.
yeah. Well, they're not all graded yet, but they will be up for tomorrow.
Because I kind of want to. Tonight I'm gonna work on my thesis stuff, so I'm probably gonna have some questions. I'm gonna try to get them together so I can ask you some questions while you're here.
Okay.
If that's okay.
Yeah, that sounds fun.
Awesome. Because that's what I know we had talked about it before, but then I realized that they don't have a matching fields. That's why I want to take the long number that says like the block group, the block, and the track, and get whatever one I need so I can make a match so I can join them
Okay.
easier. So I'm having like an issue developing my own methodology. Like I know what I want to do, but I'm getting mixed up like what steps I should do first. I think that's my big issue with it. So that's why I might need to just talk through it.
Okay. That sounds good.
Okay, awesome. I'll figure it all out tonight so I can.
Okay. So you want to do it tomorrow?
Yeah.
Okay.
I
So-
digress, so we see you.
Yeah, and then one more thing about this is that we had 40,000 records here, but like if we had 500,000 records, the other thing about using NumPy to manipulate the data is that it's like way faster.
Right.
So I was originally going to write the lab so you did the same thing in both, but we don't have that knowledge yet. But eventually we'll do that. We'll write it using a search cursor and write it using NumPy array, and you'll see the difference in that speed there.
They have some people that can write 3 or 4 lines of code and it have all of that data, like you're talking about NumPy, all of it in there, and it just saves on writing.
Yeah. So I'm gonna write the. So right now I have, here's your assignment. I'm going to write. It's just one assignment, and it's gonna say write a script that takes the tornado data and adds a new field called month. That is a.
Turn white.
It will. That is a
Just because you got it
string.
on a dark background.
And in your script, convert the values in the month in the MO field from an integer to a string representation of the month. 1 equals January, 2 equals, I don't know how to spell February, etc. And stores then in the same, what's that?
You butchered February.
Yeah, here's the straight up.
There we go. That's right. Stores them in the same. Stores them in the month. No, the month field you created. You're just going to create a new string field, and you're going to store the month coded as January, February, March, April, or May, all the way up to December. All right, so save that, and then I'm going to go to GitHub.
Process.
Yep. I should actually 25. Damn. Okay. Push. There we go. So that should be up, and
Yep, it's there.
it's there. Okay. Great. And so just to be clear, the script, the update cursor script, this script, you could really start with this script and modify this script to do what you have. So your function will be a little bit different. It'll be bigger because you'll have to say if it's equal to 1, make it January. If it's equal to 2, make it February. If it's equal to 3, so it'll be a bigger script. It'll be a bigger.
12 if thing closes?
Yes, you could actually do it with a dictionary. Like you could create a dictionary where actually it doesn't need to be a dictionary. You could create an array or a list of,
Right.
January, February, March, April, May, June, July, where the first item in the list was January, February, March, April, and then you could feed it. You could actually, but you don't have to do it this way. You can do it as a statement. You could feed it the month value, and then you could say, month list, and then you could use the quotes the brackets, and the value that's in MO. If it was 1, it would you'd have to make it so that the value that was in 1 was January.
Right.
So you could write it with 1 line of code. After you set up, you have to set up that variable.
Right. Could we do an else if statement?
Yes, you could also do an else if statement.
Kind of lengthy, but.
So would you would need 12 different ifs if you did it that way though. Like if 1, then January, if 2. You wouldn't write an else.
You technically don't need to write. You technically wouldn't need to write else if.
Yeah.
You could just write if. If it's equal to 1, do this. If it's equal to 2, do this. If it's equal to 3, do this.
I've noticed even in my other programming class, like the way that my brain understands it is if it's just lengthy and clunky. Like the clunkier it is, the more like it makes sense.
Yeah. I mean, you definitely can do that. And that's the way I was picturing it. Was it actually that way? Yeah, because you're saying.
The more information you have,
if month equals 1, return.
If MO equals 1, then return quote January quote, right? And then another if MO equals 2, then
Let's go Vincent put everything in there.
Right. Return
from the list.
But Ashley was saying, well, I think Ashley asked a question, and I said you could do it where you just have, my list is equal to January, February, ... list ends. And so then instead of, your statement could just be return my list bracket MO plus 1, or sorry, minus 1, because
is that 0?
This would be 0. Yeah. And that could be the only, so you could do this or this. So it's probably close to the same amount of typing. But there's a little bit of extra typing because you have all these if statements, right? But you also have to set up this whole variable, and so it's similar. But either one of those will work. I forgot to stop the recording over here.
That's all right.
No, I just I need to do that though because I can't leave until it's done processing, which sometimes it takes like 30 minutes. But I'm going to be around a little bit anyway, so.